Welcome. This video is CCBYNC. Welcome back, everybody. Today we're going to be solving right triangles, and we're going to use that using some trigonometry, some Pythagorean theorem, and everything else that we have at our disposal as we do this. We're going to start here with our first example, and we have a triangle here. The hypotenuse in this case is 10. One of the legs is 8, and we have an angle of 53.13 degrees. And when they say solve the triangle, what that means is find any missing angles or sides. So we know this angle, we know this angle, there's only one left. And if you remember, in any triangle, the sum of the interior angles always add up to 180 degrees, which means to find angle B, I just need to go to 180 degrees minus 90 degrees, that's here, minus 53.13 degrees, and that will give me my missing angle there. So 180 minus 90 minus 53.13, giving us that angle B is 36.87 degrees. So there's the first part. The other part is we're missing a side. Now we have a right triangle here, and we have two of the sides. That means that the Pythagorean theorem is up for grabs. So if I call this side B, then I can say that b squared, lowercase b squared, plus 8 squared equals 10 squared. Solving for B. B squared is equal to 36, which means that B is 6. And we don't have a unit on this. If we did, we would say 6 feet, 6 meters, whatever the case would be. So we have solved this triangle. We didn't even really use any trigonometry on this one, just a little geometry, a little algebra. For part B here, we have another triangle. We have a known angle of 40 degrees, and we have a side here, and the side is of length 6. So let's go ahead and get angle B again, using the little trick I showed you before. 180 degrees minus 90 degrees, minus in this case 40 degrees. And that is going to equal 50 degrees, I believe. Yep, 50 degrees. So there's one of our unknown. We're actually going to get 3 answers for this one because we have a missing angle as well as 2 missing sides. I'm going to call this side lowercase c. I'm going to call this side lowercase a. It's always opposite the angle. So we know the adjacent angle to the angle that's known, or the adjacent side to the angle that's known. And I'm going to start out by getting this a here. And that's going to be using tangent because it's the opposite over the adjacent. So tangent of 40 degrees is a over 6, which means that a is 6 times the tangent of 40 degrees. Now, before I use the tangent button on my calculator, every time I should be checking and making sure that I'm on degree mode. Now, you may have a different calculator than I have, but all the scientific calculators are going to have a degree mode and a radian mode. We don't know what radian means yet necessarily, but we will by the end of the semester, and you'll need to check it every time you do a computation. So now that I'm in the proper mode, I'm going to go 6 times the tangent of 40. And I got, and I'll round to 2 decimal places, 5.03. Once again, we don't have a unit. Otherwise, we would put, again, meters or feet or inches. So we solve for A. We are now going to solve for C. Now, that's the hypotenuse. So I'm going to compare the adjacent to the hypotenuse. That is cosine. That's the adjacent 6 over c. And after we cross multiply and divide, we end up with c is equal to 6 divided by the cosine, 40 degrees. And once again, I'm going to make sure I'm in degree mode. I can't emphasize that strong enough how many students they mix up what mode they're in and they get all the answers wrong because of it. I would hate for that to happen to you on a test or something. 6 divided by cosine of 40 degrees. And I'm getting 7.83. So that's how you solve a right triangle using some trigonometry, some algebra, some geometry. It's all kind of mixed in there. We're now going to move on to inverse trigonometric functions. So if we want to find the measure of angle T, that's this angle here. Now I have a lot of things at my disposal that I can use. I only need to use one of them, but I notice that I have all three sides in this case, and I'm going to go ahead and use the sine of T. And I know that that's going to be the opposite, which is 7, over the hypotenuse, which is 25. Now, when we say inverse trigonometric functions, what we mean by that are these three here. So we have inverse sine, inverse cosine, and inverse tangent. And those three buttons can be found on any scientific calculator. Above the sine button, you can see the inverse sine. Inverse cosine is above the cosine button, and inverse tangent is above the tangent button. Now you'll notice that it's above the button and not on a button. That means I have to hit second or shift to access that. And I'll do that here in just a moment. Inverse sine is exactly the opposite of sine. So they actually cancel one another out. So if I apply inverse sine to both sides, also known as arc sine. So you'll see that as well. And I'll address that when that comes up. And what happens here is these exactly cancel each other out. So we end up with T is equal to inverse sine of 3 over 25. Now, I want my answer in degrees, not radians, so I'm checking again. I know it seems obsessive, but if you can get in the habit of always checking, then you'll save yourself some trouble on the test. Oops, I missed the inverse symbol. Inverse sine. So here we go, inverse sine, second sine of 7. That's a weird looking 7, looks like a 3. 7 divided by 25. There we go. So this is about 16.26 degrees. Using our inverse trig. And we're going to continue with that with example 3 here. So for part A, I have sine of x equals 0.687, which means that x is going to be inverse sine of 0.687. So actually, let's once again double check there. Inverse sine of 0.687. So convenient that we have these machines that do all this work for us. 43.39 degrees. Now, as I'm doing this with my calculator, you should be trying it with yours as well while we're doing this. You can even pause the video and do it yourself. But yeah, it's better if you don't just watch me do it because everybody's calculator works just a little bit differently and I wouldn't want you to be caught off guard during a test. do part B. Tangent of x is 4/3, which means that x is the inverse tangent of 4/3. So second tangent is my inverse tangent of 4 divided by 3, giving me 53.13 degrees. So it's not, especially when your calculators do all the work for you. Now, this next part, I'm only going to go into just a little bit for now, and even where that formula comes from for the area of a triangle. In a later lesson, I'm going to show you where that comes from. It's not too hard to find. What I want to make clear is that this is the case where it's side, angle, side. So side, then an angle, then a side. So even though the letters A, B, and C aren't the same for the example here, you get the idea. It's one side, whatever A is. This will be that one side. The other side is there, times the sine of the angle that's between them. So let's try it. So the area of a triangle is going to be 1/2. And in this case, it's 8 times 13 times the sine of 82 degrees. So let's see what we get. So 1/2 times 8 times 13 times sine of 82. $51.49. And we don't have a unit on this one. This would be square, whatever, square feet, square meters, square inches. So units squared, I guess we could put. Not hard. And if you know the original area of a triangle, area is 1/2 the base times the height. You can see we're getting a little trigonometry in there when we're not quite having all the information that we need to a base or a height yet. All right, let's use the same formula, but now we're going to find the area of a parallelogram. Now, I want to make it clear with a parallelogram that if I chop this down the diagonal, I actually end up with two triangles that are actually the exact same. And you can see I have side, angle, side, so I can use the formula from above, but I have to double the formula. Right, so once I get this area, I just double that. So the area of the parallelogram is 2 times 1 times 7 times 15 times the sine of the angle between them. In this case, that is 65 degrees. And I'm going to note that the 2 and the 1/2 cancel each other out. So we end up with 7 times 5 times, check them out against degrees, times the sine of 65 degrees. And we've already doubled it, so I don't have to worry about that. So what's the total area going to be? It's about 31.72 square units. Again, we don't have units for this one. All right, next up, we have angles of elevation and depression. And what that means is relative to you looking straight ahead, if you have to look slightly up, The angle of elevation is this angle here. If you have to, as you're looking straight ahead, if you have to look downward, that is the angle of depression. And we're going to do an example right here. You are standing 20 feet away from a tree, and you measure the angle of elevation to be 38 degrees. How tall is the tree? Now, this one's a little more involved, maybe it sounds. So here's the ground. Here's you. You're on the ground. And then we have our tree. And they wanted to be clear that you are 5 feet tall. And from the top of the tree, you have an angle of 38 degrees of elevation. We also know that you are standing 20 feet away from the tree. Now that's the ground or your head, right? That's going to be the same distance, doesn't matter. And I'm going to label this X. Now, X only refers to from here to here. So my final answer isn't going to be X, it's going to be X plus 5, right? Because I got to add the, the height as part of that. So down here is 5 feet. However, I'm going to look at this right triangle here and use some trigonometry. I'm going to notice that relative to the 38 degrees, the opposite is X and the adjacent is 20. That's tangent. So the tangent of 38 degrees is the opposite, that's X, over the adjacent. In this case, that's 20. Which means that X is 20 times the tangent of 38 degrees. So 20 times the tangent of 38 degrees. And remember, that's just X. 15.63 feet, we'll say. So the tree height is X plus 5, right? X plus 5. That's going to be 15.63 plus 5, or 20.63 feet. No problem. We are to the last part. So right angles and bearings. In navigation, a bearing is the direction from one object to another. In air navigation, bearings are given as angles rotated clockwise from the north. So let me label this real quick. North, south, east, and west. So from the north, it's the angle in a clockwise direction. So this one is showing an angle of 70 degrees. So if we go to our first example here, a ship travels on a north 50 degrees by east course. So we can see the picture. Once again, this is north, south, east, and west. The ship travels until it is north of a port. So that's here, which is 10 nautical miles due east from the port which the ship originated. How far did the ship travel? We're looking for D here, this distance. Now, I'm going to notice that if this angle here is 50 degrees and all the way down is 90 degrees, Because these angles are complementary angles, that means this has to be 40 degrees. Because 50 plus 40 makes 90. I'm going to also notice that the connection between these two, D and the 10 nautical miles, is the adjacent and the hypotenuse. That means cosine. So the cosine of 40 degrees is 10 divided by D. And using a little bit of algebra, that gives me that D is 10 divided by the cosine of 40 degrees. So I have 10 divided by the cosine of 40 degrees. .05 nautical miles. Not too bad. This next one, we're going to have to draw our own picture. So we have an airplane departs from city A and travels at a bearing of 100 degrees. Let's kind of map out what that means. So once again, this is north, south, east, and west. So a bearing of 100 degrees. Now, from the north to direct east, that's 90 degrees. So we're actually beyond that. We're down here. I exaggerated that a little bit. So this angle here is 100 degrees. City B is directly south of city A. When the plane is 100 miles east of city B, so here's city A, and let's use, this is city A, and I'll call this down here city B. So city B is directly south of city A, we have that here. When the plane is 100 miles east of city B, 200 miles, so that's down here, 200 miles. This one's asking two questions. How far has the plane traveled? And how far apart are cities A and B? I'm going to go ahead and draw this out. To be clear, from north to south, that's 180 degrees. So if this is 100 of those degrees, that makes this 80 degrees. So I'm going to redraw the triangle a little bit bigger. And this is 200 miles. This one is 80 degrees. And we want to know two things. We want to know how far the plane has traveled, D, and we want to know how far apart the two cities are. This is A, this is B. Let's start with the first question. How far did the plane travel? Well, I'm going to compare, relative to the 80 degrees, the opposite to the hypotenuse, that's sine. So the sine of 80 degrees is the opposite, that's 200 over D. This means that D is 200 over the sine of 80 degrees. (200) divided by the sine of 80 degrees. That gives us about 203.09 miles. Last up is they want to know the distance between cities A and B. Relative to the 80 degrees, that is the adjacent, and the opposite, that's tangent. Tangent of 80 degrees is the opposite 200 over x, which means that x is 200 divided by tangent of 80 degrees. So we get 200 divided by the tangent of 80 degrees, giving us 35.27 miles. So how far apart are cities A and B? A little over 35 miles away from one another. How far did the plane actually go? The plane actually went a little over 203 miles.